Okay, it is often said that physics is not mere mechanics, it is sheer mechanics. Say it goes beyond mechanics to electrodynamics, statistical mechanics, thermodynamics, and all other frontier subjects. But you would have noticed that all of them just gravitate slowly towards mechanics. If any newly sprouted branch of physics slowly gravitates and settles down in mechanics, it survives as physics. If it fails to do so, it becomes something else, like technology. Electronics, for example, is a very good example, which is now outside physics. It's a very powerful branch of technology. So what I want to stress is the fact that the ancestral home of physics is mechanics. And topics like thermodynamics, statistical mechanics, electrodynamics, then say electric field is force experienced by unit charge, magnetic field is force experienced by unit current element. Then again you have thermodynamic potentials, electrostatic potential, scalar potential, and then vector potential. All those things profusely use concepts of mechanics, potentials, fields. Okay, so that aspect substantiates my statement that physics is ultimately mechanics. In Malayalam there is a word called Taravadu, that's the ancestral home. So say where you will when you visit, you will get nostalgic memories about your past, and that is the case with mechanics, because that is an area which was developed by right from Aristotle through Kepler, Galileo, Newton, say Maxwell, Boltzmann, okay, then Einstein, Schrodinger, Heisenberg, Dirac, Salam, so many people, okay. So now let us, with these words, let me plunge headlong into the theory of relativity. As all of us know, in the 20th century, physics witnessed two profound revolutions. One, the theory of relativity, which has two streams, as all of us know, special theory of relativity and general theory of relativity. And the other branch is quantum physics. Okay, now as far as special theory of relativity is concerned, well, I think since all of you may not be quite familiar with the theory of relativity, I will have some introduction even to special theory of relativity as a prelude to our discussion of general theory of relativity. Special theory of relativity, say, in fact, that word is a bit, well, English word, there is no problem, but when you translate it into Malayalam, I often see Vishishta Sabekshadavadam. In Malayalam, Vishishta means something precious, something costly, or something like a jewel. But Vishishtam, by that, what is meant is restricted. Special theory of relativity is restricted theory of relativity. Say, it tells you about theory of relativity restricted to, say, frames of reference which obey Newton's first law, that is, which are in uniform rectilinear motion, often called inertial frames. And general theory of relativity, say, goes further. It is that restriction is withdrawn, as we are going to see, and in that process, as we are going to see, gravity becomes geometry. Okay. Now, as far as let me have a brief discussion of special theory of relativity, because that will be of quite relevance here. In fact, again, I will have some comment on the meaning of relativity, because that word again is somehow, it's a misnomer. But somehow it has come to stay for the past 100 and say 20 or 15 years or so. Because theory of relativity tells you that things are not that relative as we think, they are absolute. I mean, I will say that way. It's just the other side of the coin. Apparently everybody, okay, even in popular press, they say that, oh, yeah, theory of relativity tells that things are relative, but that's a very, very misleading statement. Okay, it tells, see, I will just give you the two postulates of special theory of relativity. The first postulate is that, okay, physics looks just the same in all inertial frames of reference which move with uniform relative velocity with respect to each other. Okay, so it tells you about the invariance of laws of physics or the invariance of forms of equations of physics. Okay, in fact, it is that invariance of form of an equation is often called covariance. So physics should be covariantly formulated. Okay, that is the first postulate of special theory of relativity. The only thing is, physics as reported in, say, different inertial frames of reference, okay, should be formulated covariantly. They should have the same form. Okay, that is Einstein's first postulate. And again, the second postulate also tells you about constancy, not about relativity. It tells you that velocity of propagation of light or velocity of propagation of electromagnetic waves is an absolute constant. So these two are the basic postulates of special theory of relativity. Both tell you about absolute things. Okay, yeah, the correct name should have been, okay, the theory of physical invariance. That is a correct term, or should have been the correct name for the special theory of relativity, but somehow that word has come to stay. And again, one should remember that it's a coin which has the other side also, because as we know, space and time, they are no more absolute. That absolute nature fade into oblivion, they become relative. So one should not forget it. Okay, but remember, an interval in space-time is an absolute constant, even though space and time are relative. Okay, so and again, in say with these postulates, Einstein has clubbed or fused space with time. Okay, number one, that's the basic, that is called relativistic kinematics. Then with these concepts, if you say correct or try to correct Newton's second law, then something else happens. dp alpha by dt naught equal to f alpha, where t naught is the often called the proper time, that is time measured in a frame of reference in which the clock is at rest. Okay, so and again this is the for momentum of the particle, okay, which has, say, P alpha has, well, first I will use Minkowski component. Later I will shift to contravariant covariant components, P3, P4, where P4 is IE, say. Well, in correcting this, you will get that the fourth component of momentum is nothing but the energy of the particle, okay, multiplied by I by C, where I is root of -1, C is the velocity of light. So I won't go into the details. This is called the relativistically corrected form of Newton's second law, into the details of which I won't go because of the shortage of time. In correcting Newton's second law relativistically, you will get a new quartet. See, the starting point is x alpha, x1, x2, x3, x4, means x, y, z, ICT. Okay, you can put it like this: x1, x2, x3, x4, or x, y, z, ICT. This is a kinematical quartet, okay, which embraces a trio and a singlet, okay, space coordinates x, y, z, and time multiplied by IC, okay, because the basic, all these stem from the fact that x alpha equal to minus, say, x alpha equal to 0, because by this I mean, just expand it, x1 plus x2 plus x3 plus x4, because this goes without saying, alpha equal to 1 to 4, okay, equal to 0. That means x square plus y square plus z square with x4 ICT minus c square t square equal to 0, which means x square plus y square plus z square by t square equal to c square, which is equal to x prime square plus y prime square plus z prime square by t prime square. Well, see, it is this which is written here. In other words, this is the basic second postulate of the Einstein's special theory of relativity, which establishes that space and time are fused together. With these tools, if you correct Newton's second law, you arrive at the dynamical quartet, P1, P2, P3, P4. It fuses momentum and energy into a single entity. Now, of course, I won't go into the details of all these things, because this is just as a prelude for the discussion of general relativity. I will just, with this, you couple the equation of conservation of charge, del dot J plus dou by dou T of rho. I hope everybody is familiar with this. Say, divergence of current density equal to negative time rate of change of charge density. It is just conservation of charge. This is a conservation of charge is a basic thing to which, if you apply this kinematical, say, fact, you will get, it implies that current and charge densities will form another quartet. Okay? If current density components will transform like space, charge density will transform like time. If momentum components will transform like space, then energy component will transform like time. Okay? So you have now met one kinematical, say, set of things, namely the quartet XYZ ICT, which is the starting point, okay, of special theory of relativity. The second one emerges by when you introduce the relativistic correction to Newton's second law, you will get that fuses momentum and energy. Then with this, if you again couple with the equation of continuity, you will arrive at the fact that if current density behaves like space, charge density behaves like time. Again, one more thing is, you know that current density causes the so-called vector potential and charge density causes scalar potential. So again, Ax, Ay, Az, and the special theory of relativity, it fuses space and time, momentum and energy, current density with the charge density, vector potential with scalar potential, okay. So it's a very powerful unification. And again, maybe one more thing I will write, just divide all these things by Planck's constant, you will get the wave vector components kx, ky, kz and I omega by c. This is omega is 2 pi nu, the so-called temporal time frequency, okay. So see, wave vector components or spatial frequency components are fused with the time frequency components, okay. So this is just the same thing as this, but for the fact that if you divide all these things by Planck's constant, you will get this. So that is nothing new, okay. With this, let us now go to, with this as background, of course, one more thing which I have forgotten to quote, but it is everybody's knowledge is, another byproduct or bonus in correcting Newton's second law is the famous result. If you correct Newton's second law relativistically, you will get two famous results. One is very glamorous, okay. Everybody in this world of ours seems to know that E equal to mc square, okay. The other is the fact that, as I told you earlier, energy is nothing but the fourth component of the four momentum, or energy and momentum are fused together, which is less glamorous. All the same, it goes into the very heart of, say, relativistic quantum mechanics and everything. Okay, now let us go. I think I need not go into the electromagnetic field. See, these things will Lorentz transform. See, maybe that will be worthwhile quoting. He suddenly, just something like a premonition, he got the idea, when one freely falls, one does not feel weight at all, okay. A freely falling person, maybe I will write it. This is Einstein's happiest thought. He suddenly, that idea flashed through his mind. When one freely falls under gravity, one does not feel gravity at all. Okay. The important thing about this is, it's apparently a harmless statement or innocent statement, or rather useless statement, but it conjured up in Einstein's mind the experimental findings of Galileo long back. Okay, he had established that inertial mass and gravitational mass are just equal always. There has not been any example which disproves this thing. I will write it here. and that is related to this. Inertial mass. Equal to gravitational mass. This was established long back by Galileo through his experiments. Apparently, well, usually one has a tendency to ignore this. In fact, I will quote a very interesting example. Go to Himalayas, okay? Then follow the rivers like Alakananda, Mandagini, Bhagirathi, Yamuna, etc. Go upstream, okay, through Bhagirathi, okay, goes through Gangotri and finally to Gomukh, where there is just water sprouting, just gushing up from some spring. See, nobody will believe that it is going to become the mighty Ganges a bit later after going through a series of prayagas like Vishnu Prayaga, then Rudra Prayaga, Deva Prayaga, and Allahabad, the famous Prayaga and all that. Okay? Or quoting another example, it is something like some silly or apparently unimportant fact which just proves an important clue to the solution of some criminal case or detection of some famous criminal case, something like that. See, inertial mass is gravitational mass. What has that to do with general relativity? Okay. See, just okay. See here, d square x by dx square, that is mass into acceleration. Say this introduces the so-called inertial mass, because with the application of a given force, the acceleration is inversely proportional to the mass. The greater the mass, smaller is the acceleration for a given force. So it's just a reactionary sort of thing. This inertial mass, it plays a passive role, not an active role. It is defined, say, in a context like this, and the force here can be anything. It can be gravitational force, electrostatic force, magnetic force, surface tension, force of friction, anything. See, it is so general, this inertial mass, and again, it plays a passive role. Compare this or contrast this with the force of attraction between, say, a mass m with the mass of the earth. Okay, g m by r square with a minus. Okay, this is the gravitational force of attraction between, say, either the sun and the earth, or between the earth and some piece of stone or whatever it be. Okay, say this is Newton's universal constant of gravitation. Okay, here this force is quite different by way of its definition. Okay, it plays an active role. The bigger the mass, the bigger the force. Okay, see, here this mass, inertial mass, plays a passive role. This mass plays an active role. To distinguish this, I will write here mi, inertial, m here mg. Okay, say g, mg, m r square. This is restricted to specialized to gravitational force. Now, so that suppose in a situation where the relevant force is the gravitational force of attraction. So what happens is g mg m by r square equal to mi, because if the force is the gravitational force, this is the acceleration due to gravity. So, see, G equal to Gm by R square into Mg by Mi. Acceleration due to gravity is, it involves this ratio Mg by Mi. But then in all experiments conducted so far, say, it is found that acceleration due to gravity is Gm by R square, which implies that Okay. We have been talking about the fact that the inertial mass, which is defined in a very general context, in all cases just becomes equal to the gravitational mass, which is defined in a very specialized context of gravitation. As a consequence, for example, when one freely falls, one does not feel gravity. Consider a cabin. Okay, say I am just in this, I am freely falling. Okay, then some body, maybe a stone is falling, a feather is falling. When, say, because of the fact that the gravitational mass is equal to the inertial mass, as Galileo proved long back, all bodies fall with the same acceleration, okay, on a free fall. Okay, so when I fall freely, okay, I feel that this is just floating. This stone is floating, this feather is floating. There is, say, nothing moves faster, all just floating. Okay, and again, suppose we are in the Earth's gravitational field, okay, on the ground. I feel gravity, okay, downwards. Just compare this with the situation when we are in a far off place, very far off from any mass, or that is in outer space where gravity is nil. What will happen? You will feel that all of, say, the person, the stone, the feather, everything is floating. Okay, exactly as during a free fall. And again, suppose in the outer space where there is no gravity, this is accelerated upwards. Then what will happen? See, in the outer space, a cabin which carries me and, say, some other, some other body like a stone or something, this feather, everything. Okay, when I am when the cabin is accelerated, okay, see, the relevant force here is, it need not be, it has nothing to do with gravity. It can be any force. It can be electromagnetic or whatever it be. Okay, compare this thing when the same cabin is standing on the surface of the Earth. When I feel gravity, the same person here, okay, feels gravity. Okay, yes, but here the force is purely due to gravitation. Okay, and the situation is, see, whatever I feel here, okay, this is on the surface of the ground where gravity works. Gravity acts downward. This is in outer space, the same set of people, objects, etc. Okay, in a similar cabin, in a far off place where there is no gravity but which is accelerated, one will feel, one can't distinguish between this and this. The same physics is reported here as it is here. Okay, this is the so-called Einstein's principle of equivalence. Principle of equivalence says that the consequences of gravity in an unaccelerated cabin or accelerated system as it is here is exactly the same as the force which we feel when it is accelerated upwards, okay, in the absence of gravity. You can't distinguish, okay, these situations. In other words, gravity and acceleration. See here, when it is on the surface of the Earth, it is gravity, G. When it is outside the domain of gravity, it is general acceleration. One can't distinguish. Principle of equivalence says that acceleration, okay, gravity, say, cannot be gravity without acceleration and acceleration without gravity are just one and the same. You can't distinguish. This situation is exactly similar to the case of different inertial frames in the special theory of relativity. You have, say, the so-called, I will just quote this one. The familiar example of a moving train. See, I have, we people are stationary here and a train is moving with a velocity v, okay, along the x direction. This is the train, this is us people who are stationary here. You can't distinguish by no experiment performed, say, in this will show which is moving, which is at rest. You can't. Okay? That is Einstein's first postulate in special theory of relativity. Physics looks just the same in all inertial frames. This is glorified here in general relativity. Instead of inertial frames, you have freely falling frames. Freely falling frames replace inertial frames in special relativity. The role played by inertial frames in special relativity is played by freely falling frames. See, when I drop this, this is freely falling. And again, we people are freely falling. I mean, along with the earth, we are freely falling to the sun. The moon is freely falling to the earth. Because the very high initial velocity, it just, say, maintains its motion. They are all cases of free fall under gravity. So, free fall under gravity, okay, different examples of free fall under gravity cannot be distinguished at all. So, this is that stems from the principle of equivalence, which says that gravity, okay, and accelerationless, gravity without any acceleration and acceleration in a place where there is no gravity are fully equivalent, okay. That is called the principle of equivalence. Principle of equivalence, plays the role of second postulate of special theory of relativity. I told you in the beginning, special theory of relativity has two postulates. One, that of covariance. The laws of physics should have the same form in all inertial frames. Number two, velocity of light is an absolute constant in all inertial frames. Okay. Instead of that, in general relativity, you can have the entire general relativity, okay, framed using these two postulates. One, principle of equivalence. Okay. That is, gravity cannot be distinguished from acceleration. No experiment done in different freely falling frames can tell them apart. They all look alike. Okay? Because you have noticed some important peculiar features of gravity. It is terribly smaller than any of the known forces. Electromagnetic force is something like 10 raised to 36 or 39 times as big as gravitational force. Okay, strong force is still bigger. Even weak force is substantially way bigger than gravitational force. Gravitational force is so small that it makes its presence felt only when at least one of the parties is not even microscopic, mega, like it should be a celestial body like the Earth. Okay, so that is one peculiar property of gravitation. The other thing is, gravity is always attractive, quite unlike the electromagnetic forces where light charges repel, unlike charges, okay, attract. Okay, parallel currents attract, anti-parallel currents repel. So you will have all sorts of randomization happening within the domain of electromagnetic field. That is why in the long run, okay, it is like something like the so-called rabbit and the tortoise. The slow tortoise ultimately wins the race. Gravity is the ultimate winner because of the fact that there is no civil war within the gravitational domain. It is slow but sure, and but electromagnetism is so big, but there is so much of civil war happening, so that ultimately it just comes down to nothing. Okay, in the long run, electromagnetism is of no consequence. So gravity is the ultimate winner. It is so feeble, and again, it's an intensive parameter. As we have seen, gravity does not depend on the mass of the particle. All masses, as we have seen, they just fall with the same acceleration. Okay, that is why gravitation or acceleration due to gravity is an intensive parameter. It does not depend on the amount of matter. And again, since there is no fight happening inside the domain of gravity, that is all gravitational forces are attractive. Okay, Einstein surmised, okay, concluded that it should be a property of, you have the fundamental things like mass, length and time. And we have seen gravity, it has been proved that gravity does not depend on mass at all. Right from Galileo we know that. So Einstein concluded that, so gravity should be a universal property which depends on space and time alone. Okay, that is Einstein's conclusion. So I will write if you want to, well, I am putting it in very popular terms. I am sacrificing a lot of rigor here, because if I have a choice between rigor and clarity, I think I feel it's better to have more clarity than rigor. Okay, so the first postulate is the principle of equivalence. The second, okay, postulate, you can take it, the principle of general covariance. Basic principles or postulates of general theory of relativity. Always it is interesting to juxtapose this with the special theory of relativity, because I repeat it just to make it more, to make it clearer. First postulate of special theory. See, laws of physics should be covariantly formulated. Of course, there it is restricted to inertial frames. Okay. Instead of, and here you have, that appears something like the shadow of that. This principle appears as the shadow of that principle in special theory. Principle of general covariance, where by general I mean, instead of inertial, restricting to inertial frames, you have freely falling frames, which embraces any branch of gravitation. Everybody freely falls with respect to his neighbor or something. The earth freely falls. A satellite sent by our country, say it freely falls. Because of the very high initial velocity, it continues rotation. It really freely falls. All freely falling bodies, okay, kind of saying all freely falling bodies have the same physics, something like that. Okay, and acceleration, okay, say cannot be distinguished from gravity. Gravitation cannot be distinguished from a general acceleration because of the fact that it follows from inertial mass equal to gravitational mass. All bodies freely fall under gravity, okay, say without any relative motion at all. Okay, this is so Galileo reborn, okay, in the world of Einstein. Okay. The other is, yeah, principle of general covariance. You know that maybe all of you who would have been familiar with tensors, vectors, etc., would have seen that, see, vectors with respect to rotation, the components will go on changing in a specific way. Okay. Tensors, second rank tensors will transform like second order products of components of vectors. A third rank tensor will have its components transforming like third order products of components of vectors. Well, I am quoting this in very, very simple say terms to make things clear. I am fully aware of the fact that I am sacrificing a lot of rigor here, but say that this drives home the basic physics. So, yes. See, a universal statement is, see, for example, suppose I will ask a very simple question, even high school students will. Suppose I write well, everybody among you will question this. This is wrong. A dot B equal to C, where A, B, C are vectors. See, I have purposefully omitted this arrow. This is the scalar part of it. Okay, I mean, so maybe, sorry, A dot B is a scalar. So, okay, now it is correct. This is a wrong statement. Will you agree? Scalar product between two vectors, it should be a scalar. Here I have a vector. We say, a relativist will immediately say, oh, this is a violation of covariance. Covariance is violated. Okay. Similarly, you know that, for example, if you have two polar vectors, suppose A, B, C are polar vectors, and I say that A cross B equal to C, where I give you the idea A, B, C are all polar vectors. Again, that is a wrong statement. Covariance is violated. If A and B are polar vectors, A cross B is an axial vector. But axial vector cannot be equal to a polar vector, because under inversion, the polar vector will change sign, axial vector won't. So there is covariance violated. Okay. So this is the simplest, say, I will say this of course a vectorial statement or scalar, this is a scalar statement, this is a vector statement. Both wrong. Okay. Such statements, of course, they can be corrected, and the correct statement is called, say, covariant statements in general. For example, see, if Tij is a tensor, second rank tensor, it transforms like Aik, Ajl, Tkl. This is the correct covariance of a second rank tensor, varying like second order products of components of vectors. Okay. What I wanted to convey by these things is simply to focus your attention on the fact that for communication of ultimate truths in physics, one should have tensorial statements. Okay. One should have, say, statements in the form of tensors. Okay. And of course, that includes vectors and scalars. Okay. Scalar is a tensor of rank 0, vector is a tensor of rank 1. But of course, there are complications. I just forgot all those things. There are two types of, say, tensors, contravariant and covariant, okay, tensors, contravariant, covariant vectors, etc. So it is hellishly complicated, but I don't go into such unnecessary details at this juncture. Okay. A statement should be covariantly formulated, then it is always correct. Okay. Einstein, he was fully, see, by his special theory of relativity, he proved that, okay, if physics looks just the same in all inertial frames of reference, say, they should be, say, they can be covariantly, say, expressed, that is the familiar Lorentz transformation of scalars, vectors, tensors, etc. You know that a scalar thing will Lorentz transform into itself, say its Lorentz invariant. Vectors will have its Lorentz transformation, components transforming like the familiar Lorentz transformation of space and time. Tensors will transform in a more complicated fashion. For example, electromagnetic field. Electromagnetic field is an antisymmetric second rank tensor in 4-dimensional space. Okay, so say there is extra complication, all the same they will Lorentz transform. They will Lorentz transform in a very specified form. Then nobody can question their absolute statements. Okay, so laws of physics should be covariantly communicated or expressed. Okay, along with the experimental fact that inertial mass, and because of the fact that inertial mass is exactly equal to the gravitational mass, okay, you have the principle of equivalence. Gravity and gravity without acceleration and acceleration without gravity, they cannot be told apart. They cannot be distinguished. Okay, so these are the okay. That is the basic physics of general theory of relativity. But this happened, as I told you, this premonition occurred to Einstein in the year 1907. Then comes the nightmarish aspects of the problem. Einstein was so much jubilant, as I told you. He called that thing the happiest thought in his life, the principle of equivalence. But he wanted to express that in a general covariant fashion, in the language of tensors. Okay, and that proved so hellish. Okay, and it took for him 8 years from 1907 to 1950, with of course occasional excursions to say ideas of quantum physics, photoelectric effect, okay, etc. He just took excursions in the meantime. But say in general, the year 1907 to 1915, they proved the basic formative years of general theory of relativity. He was trying to express this thing in the language of general covariance. Well, he found one more thing which for further discussion I would like to have a brief hint of. I told you that gravitation, since it is no more a function of, it does not depend on mass, it's an intensive parameter, it's a basic property of space-time because it is an intensive parameter, it is cumulative, it never has any civil war within. Okay, these aspects forced Einstein to conclude that yes, see, it's a property of space-time. What sort of property? That was the next question. Well, to get a very simple clue to what is happening, for example, under free fall, where this is the acceleration due to gravity, this is free fall with the initial velocity 0, that is free fall under gravity. See, the second derivative of this will be just g, okay, d square s by say dt square. That is something like second derivative. First derivative is something like a slope, the second derivative is curvature. Okay, so the property which Einstein was in search of had the nature of curvature of space-time. But remember, in the year 1905, Einstein already had established 4-dimensional space-time, that is given by, as I told you in the beginning, x mu equal to 0. That is second postulate of special theory of relativity, constancy of velocity of light. Okay, so 4-dimensional say space-time was very much established in the year 1905 itself by way of special theory of relativity. So people were fully at home in the language of four-dimensional space-time. So what happens is, can you think about second-order derivatives in such a world of four-dimensional space-time? See, in a single situation like this, I have this is second-order derivative of S with respect to t, d square by dt square of this thing. Okay. Now, in four-dimensional space, Einstein naturally found that. See, I will just schematically tell you or show you G. In one-dimensional space, you will have, say, G, which is, I am pleased to call it G11, goes to, in two-dimensional space, it goes to G11, G12, G21, G22. Curvature components in two dimensions. Well, these are sacrificing a lot of rigor. I just drive home the basic fact. Okay. In three-dimensional space, it goes to G11, G12, G13, G21, G22, G23, G31, G32, G33, 9 components, and ultimately in the actual four-dimensional space of ours, as was established by special theory of relativity, you have the curvature components G11, G12, G13, G14, G21, G22, G23, G24, G31, G32, G33, G34, G41, G42, G43, 16 components. Okay, this thing is called the metric. Okay, it's a matrix which displays all the components, but things are substantially much simpler than this because of the basic symmetry. One can show that the whole thing is a symmetric matrix, so that 3,1 and 1,3 are just the same. Similarly, 2,3 and 3,2 are just the same. So this gets considerably simplified. This part will wither away. One can just forget it. Of course, that means you have it here. It is G12. This is G22, G23. This is G31 is G13. Okay, that's the meaning. So there are only 10 independent curvature components in four-dimensional space. Okay, and of course, if you ask how can we have, say, curvature components in flat space, the answer is certainly no in the presence of mass. Say space is curved. Okay, it's no more flat. Okay, so that this equation which I have written earlier, I will write it here. Yes. See, x mu. I hope I need not explain this frequently. It goes without saying, mu equal to 1 to 4 means it implies x square with x1, x square, x2, y square, x3, z square, then x4. I told you x4 is ICT, so minus c square, t square. See, this layman statement is written in sophisticated language. Of course, I have written this in Minkowski components. You know, there are it is plagued, relativity is plagued by different set of, because of shortage of time, I may just have only a passing mention. This could as well be written as well. The only thing is it will just give you some complication, but it is in fact simple. Maybe I will just illustrate one example. Okay, this thing. This is another way of writing the same thing. This means second postulate of special theory of relativity, constancy of velocity of light, x mu, x contravariant mu into x covariant mu is 0. Okay, it is something like scalar product, A dot B is 0, they are said to be orthogonal. Okay, the only thing is here the space is having, say, the one part is always negative. Okay, so this simply means, of course, this is contravariant covariant language. I will write it like this. See, instead of 1, 2, 3, 4, here you have mu equal to 0, 1, 2, 3. That's the convention. Means, see, x0 plus x1 plus x2 plus x3 equal to 0. Then, see, x0, see, 0 replaces 4 here. I am helpless because I can't do anything about it. Okay, 1, 2, 3, 4 go to 0, 1, 2, 3. That 4 goes to 0. Okay, x0 equal to ct. Okay, then x1 equal to x, x2, see, it is never x square, it is x2, beware. x2 equal to y, x3 equal to z. And then these are called the covariant components, okay, in flat space. Okay, say x superscript 0, x1, x2, x3. The corresponding these are the contravariant components. Now covariant components are x0 equal to minus x0 equal to minus ct. Well, I will explain this further. Okay, x1 equal to x superscript 1 equal to x, x2 equal to x2 equal to y, x3 equal to s superscript 3 equal to z. Okay, so that, see, this is written like this. You have ct x y z contravariant components. This is minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. This covariant vector components are obtained. Okay, see minus ct x y z. Well, even here some authors will make it more complicated. I remember John David Griffith. Well, he is a very, very good author. But I remember when he writes electrodynamics, his book entertains this system. When the same author does a book on particle physics, he just puts this plus 1, minus 1, minus 1, minus 1. The physics is just the same because it is, if x square plus y square plus z square minus c square t square is 0, minus x square minus y square minus z square plus c square t square is as good as 0. So there is no, it's a matter of, say, people using different conventions. That's all it. So you can get familiarized by repeatedly doing, say, problems or reading books. Okay, so this is called, say, this is contravariant vector components in flat space, Cartesian components in flat space, covariant vector components, this is called metric tensor. Okay, metric means related to space. Okay, measure of space, metric tensor in flat space, Cartesian, say, flat space, metric tensor. I can write this for, see, as I told you, A dot B, say, you have done in quantum mechanics, the scalar product between two vectors A and B is AI star Bi, not AI Bi. Remember, you just star the prefactor, bra vector factor. Okay, something similar you can understand here. Okay, that is x mu equal to x mu equal to, remember, suppose I write equal to x mu equal to 0. It's a very interesting statement. All amount to the same thing. Either this is this and this. See, A dot B is B dot A. Okay, x mu expand it, you will get the same thing equal to 0. Okay, so this is covariant components, contravariant components, contravariant into covariant. If I write it like this, it is Minkowski, 1, 2, 3, 4. See, if you see this, you can immediately see this is no contravariant covariant business, this is just Minkowski. This is contravariant, but all amount to the same thing. It is second postulate of special theory of relativity, constancy of velocity of light. That is mathematically expressed like this. We say that light, okay, say has associated with it a null vector. Okay, its norm is 0 by its very nature. And then if the tilt is towards positive quantities, we say it is space-like interval. If the tilt is towards negative quantities, you have time-like interval. This world of ours is, fortunately or unfortunately, is a time-like world where law of causality is valid. All these things are typical of special theory of relativity. Okay, why I quoted this thing is, this metric tensor in massless flat space becomes more complicated, okay, in space around the masses. In the presence of masses, say, as I told you, see, these curvature components tell you that, see, in this, just compare this. If it is flat space, I will say minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, the same thing. Okay, as far as flat space is concerned, that is, if space-time is uncomplicated or unpolluted by matter or by mass, you have simple, the metric tensor is as simple as this. While in the presence of matter, it gets complicated. I will write that complication in the following way. See, basically, remember scalar product, x mu, maybe shall I write it like this? Okay, x mu, 0, 1, 2, 3, 4. I'm sorry, 0, 1, 2, 3. Okay. Remember, just stretch your imagination and I write here where x mu equal to g mu nu x nu. See, it's quite clear. Okay, in simple terms, even without going into all its complications, I can say that it's a contraction in the language of vectors and say tensors. Say a contravariant vector is mapped into a covariant vector by this thing which is called the metric tensor. In general, the metric tensor has 10 components in the most general case, because even though it is 16 because of symmetry, it is only 10. 4 plus 3 plus 2 plus 1, 10 components. Metric tensor has 4 components, and only in flat space it so happens that this is, if it is minus 1, these 3 are 1, or if it is plus 1, these 3 are minus 1. That depends on your choice. All the others just become 0. Okay, so this is called, this is the metric tensor, G mu nu. It's a covariant second rank tensor whose components are functions of space, okay, and time, okay. And so where are we now? Remember, we have seen that gravity, okay, manifests in the form of curvature, okay, second order derivative. Curvature, there are 16 components which boil down to 10. So gravity just becomes geometry with 10 components, okay. The geometry is fully communicated by, to us by the so-called metric tensor, okay. That is this thing. Yes. Now let me go back to autobiographical elements of Einstein. Okay, here it's a turning point. So far Einstein was perfectly confident. But the space is, it's a curved space, no more flat space. And if you want to do the calculus, okay, or that so-called differential geometry of curved space, the curved space is called Riemannian space. It was hellish or nightmarish. It's so complicated. Okay, Einstein was terrified, in fact, because with all his genius, he could not grasp the mathematics of this curved space. Okay, now comes Marcel Grossman. Okay, Grossman, as maybe you may be remembering, was a classmate of Albert Einstein. Okay, and in fact, there's a funny thing. They were always sitting side by side. Einstein was more, he was so mathematical minded, but in other classes like history, languages, he was a bit lazy. Okay, but Grossman fully realized the potential of Einstein, and he said in the classes, "Oh, this Einstein is going to become a great man one day." That's the statement of Grossman. Okay. Then after matriculation, Einstein pursued, physics, chemistry. Grossman pursued mathematics, specialized in mathematics. Okay. Then finally, they both landed, in the same office, patent office in Bern, in Switzerland. Okay. They were working as patent inspectors. Okay. Then one day, as I told you, the physical idea was born in the mind of Einstein in 1907. But he was so much unhappy about his mathematical ignorance, something like that. Okay, in spite of his genius in physical ideas. One day he was frantically in search of Grossman. Okay, Grossman, you should save me, or I will go crazy. That is the words spelt by Einstein. You should save me now. What's the problem, Einstein? He said, see, there's a problem. I have a very wonderful idea which I would like to express in mathematical language. I could not. I can't. Then Grossman asked Einstein, let me see your problem. He said, okay. He said, oh, this seems to be the mathematics of Riemannian geometry. But don't worry, Einstein, I have specialized in Riemannian geometry. It so happened, see, Marcel Grossman had, after his graduation, he was doing research in Riemannian geometry. So then started the long and very, very, very fertile collaboration between Marcel Grossman, Albert Einstein. Okay, the mathematics is too much for me. I can't do anything about it. Okay, so I will just say best of luck to you on this context. I can't, because it is so terrible. I will just quote the history, okay, of curved space. The history starts from Carl Gauss, the great mathematician who started. Next is Riemann. Of course, it is actually the curved space geometry is often called as Riemannian geometry, even though his guru was Gauss. Now comes Christoffel. These are the surnames. I don't know the first names, they are very complicated. Okay, Christoffel. Okay, I mean the mathematical ideas flowed from Gauss via Riemann to Christoffel, then Ricci. I don't know whether it is Ricci or Ricci. Pronunciation I don't know. It looks like Ricci. Ricci tensor. Okay. Then Marcel Grossman, Einstein's collaborator. Well, Grossman's role is not as a researcher. He did not create any new mathematics. He just thought this entire legacy was passed on to Einstein by Grossman, Marcel Grossman, who was classmate and colleague of Albert Einstein. Okay, and Marcel Grossman. Then, of course, I will say right here Einstein. Okay, and the period is 1907 to 1915, November 25th, 1915, when they published their combined paper, okay, the Einstein-Grossman paper on general theory of relativity, where I told you principle of equivalence was, and its consequent conversion of, say, gravity into geometry was, say, it just blossomed into a very fertile mathematical language, that of Riemannian geometry. Okay, the differential geometry in curved space. Okay, that part of it I will just bypass. It is beyond me. Okay, and I write the famous Einstein equation for that curvature. This is the famous Einstein's field equation.
Maybe you have a photo section.
Oh, sure. Okay. Okay. So I will stop now. Okay.
Then we will continue after.
Okay. We will.